given a point B and a plane, we want to find the point in the plane that's closest to B. So here's a plane and a point, and we want to find the point in the plane that's closest to this point. Now, by translating the plane and the point, we can ensure that the plane contains the origin, in which case it's a vector space. It has a basis. Let v1, v2 be the basis for this vector space. Then our goal becomes, given a point B and vectors v1 and v2, find the point in the span of v1 and v2 that's closest to B. Here's the point. For example, suppose v1 and v2 are these two vectors, and our point B is this. Then the point in the plane closest to B is 6, minus 3, 0. So we want to come up with an algorithm that will solve problems of this form. More generally, given a vector B and vectors v1 through vn, we want the algorithm to find the vector in span of v1 through vn that's closest to B. Now, as a special case, we could use such an algorithm to decide whether B lies in the span of these vectors v1 through vn. After all, if the vector in span of v1 through vn closest to B is B itself, that means that B is in the span. If not, then B is not in the span. So let A be the matrix whose columns are v1 through vn. And using the linear combinations interpretation of matrix vector multiplication, a vector in the span of v1 through vn can be written as A times x. Thus, testing if B is in the span of v1 through vn is equivalent to testing whether the matrix vector equation Ax equals B has a solution. More generally, if Ax equals B possibly doesn't have a solution, we can use the algorithm to find the point in this set that's closest to B. Now, so far we've just discussed finding the point itself, but we also want to be able to find out how to express it as a linear combination of v1 through vn. That is, we want to find the vector x that solves this equation, or that minimizes the distance between Ax and B. So, as I'm saying, it's not enough to find the point in the span of these vectors that's closest to B. We want to find the representation of that point in terms of those vectors. So our goal is to find the coefficients, x1 through xn, such that the linear combination, x1, v1, and so on, is the vector in the span of these vectors closest to B. I can write that as minimizing the norm of the difference between the vector B and the product of this matrix with this vector. And that's equivalent to minimizing not the norm, but the square of the norm. And we can rewrite this matrix not in terms of its columns, but in terms of its rows. We've written it here, where the rows are the vectors a1 through am. Then this problem is equivalent to minimizing this sum of square differences. And this is the problem that we addressed in the, with gradient descent. All right. So finding the vector x that minimizes this norm squared, which is equivalent to finding a vector x that minimizes this sum of square differences, this is called least squares. It goes back to Legendre, sometimes attributed to Gauss. An equivalent way of formulating the question is, given a matrix vector equation, Ax equals B, in case that equation doesn't have a solution, find the best solution available. Find a solution that minimizes the error, where the error is the difference between the target vector B and the vector Ax that you found. You want to make that error have as small a norm as possible. Now, there is an algorithm based on Gaussian elimination, but we're going to develop an algorithm based on the notion of orthogonality. And we'll see that you can get solutions much, much faster than, say, gradient descent.